In many chemistry textbooks, the molar volume of a gas is defined as the volume that 1 mole of gas will take up for a given state. This is easier to see as a ratio and honestly more helpful for calculations. Consider the ideal gas equation. If you rearrange the equation by dividing both sides by moles, and then also dividing both sides by pressure, you will end up with the ratio of volume per mole being equal to the gas constant times temperature divided by pressure. This means we only need 2 pieces of information to know what our volume to mole ratio will be: the temperature and the pressure. For many first-year chemistry gas problems, we consider situations at standard temperature and pressure, which is frequently shortened to an abbreviation STP. At this state, the temperature is always assigned as 273 Kelvin, and the pressure is assigned at 1 atm. Let's plug these numbers into our volume to moles ratio. We have our gas constant, 0.08206, with units of liters atms, divided by mole Kelvin. We have our standard temperature, 273.15 Kelvin. And we have our 1 atmospheric pressure at the bottom. If you perform this calculation, you'll arrive at a very common number used for gas stoichiometry problems, that the volume to mole ratio is 22.4 liters for every mole of gas. It's important to remember that this molar volume approximation works well only for ideal gases. If the gas you are considering is large or polar or both, you probably need fancier equations to help you out. We can use ratios like the volume to mole ratio being 22.4 liters of gas per mole of gas in pretty much any stoichiometric calculations involving gases. For example, let's say we want to heat up some baking soda to show some clever young people a cool chemical reaction. A gas stoichiometry question could ask something like, how many liters of carbon dioxide are produced when 123.4 grams of sodium bicarbonate decomposes at standard temperature and pressure? Okay, first of all, I'm going to need to make a plan to attack this type of question. I need to know the molar mass of sodium bicarbonate so that I can get rid of these awful gram units. So I'll consult my handy-dandy periodic table, and I calculate that the molar mass is 84.01 grams per mole. Now I can set up a standard dimensional analysis problem. We're starting with 123.4 grams of sodium bicarbonate, and we'll use the molar mass, 84.01 grams of sodium bicarbonate per mole, to convert our original number into moles. And now we can change from moles of sodium bicarbonate to our molecule of interest, the carbon dioxide, This happens to be a 2-to-1 ratio in this case. So we'll write 2 moles of sodium bicarbonate and 1 mole of carbon dioxide gas. And now we can use our new molar volume at STP to convert from moles to liters. So we'll put our 22.4 liters of gas at STP for 1 mole of gas at STP and finish up our calculations. So here we go. We'll get 16.45 liters of carbon dioxide. When you come across a gas stoichiometry problem that does not occur at STP, where we can't use our really fun volume to mole ratio, you need to just take a deep breath and break down your problem into 3 individual pieces. Step 1, you need to find moles from your starting information and check for any limiting reactants. Step 2, use a mole to mole ratio to change into the desired chemical units. Step 3, this is where it's different. Use PV equals nRT to calculate the volume in liters. If necessary, you can change the volume units from there using your dimensional analysis skills. Do a few of these practice problems from your textbook and you should be golden.